Okay. Good morning students, very good morning. So today we have lecture number 3 on alternating current for second year students. Okay. So now in the previous class we have studied about the alternating current, alternating voltage applied to an inductor, alternating voltage applied to a resistor. When an alternating voltage is applied to a resistor, the voltage and current both are in phase. There is no phase difference between the voltage and current when there is a pure resistor in the circuit. That is, the voltage and current will be flowing simultaneously, and then when a inductor is placed, that is for a pure inductor, so then the alternating current lags behind the voltage. When there is an inductor in the circuit, then we found that the current lags behind the voltage by an angle of pi by 2. The current lags behind the voltage by an angle of pi by 2. That is, there exists a phase difference between the voltage and current when there is a pure inductive circuit, and there is no phase difference between the voltage and current when there is a pure resistive circuit. And now today we shall study alternating voltage applied to a pure capacitive circuit. Alternating voltage applied to a pure capacitor or capacitive circuit. So now what happens when alternating current is or alternating voltage is applied to a pure capacitor? Consider a capacitor of capacitance C. Consider a capacitance of capacitor of capacitance C connected to an AC source. Connected to an AC source as shown in the figure. Connected to an AC source as shown in the figure. AC source. And now, as a result of this AC source, the capacitor periodically gets charged and discharged. Due to the AC source is connected, the capacitor periodically gets charged and discharged. So charging and discharging takes place, continuous charging and discharging takes place in the capacitor. Okay. So now the EMF applied to the EMF applied, that is the alternating voltage applied, the alternating voltage applied to capacitor is given by V is equal to V naught sin omega t. V is equal to V naught sin omega t. Call that the equation number 1. So the potential difference across the capacitor, the potential difference across the capacitor is Vc is equal to Q divided by C, where Q is charge at any instant, where Q is charge at that instant, charge at any instant. At that instant we have applied the potential difference across the capacitor at any instant. At any instant. Okay, say it as at any instant. The potential difference across the capacitor at any instant is given by Vc is equal to Q divided by C, where Q is the charge at any instant and C is the capacitance of the capacitor. So now at any instant of time, the potential difference applied across the capacitor must be equal to the applied EMF. That is, potential difference across capacitor must be equal to the alternating EMF applied to the circuit. So therefore potential difference of capacitor is Q by C, and alternating voltage applied is V naught sin omega t. That is, Vc must be equal to V. that is Vc must be equal to V, and Vc is Q by C and V is V naught sin omega t. So therefore charge at any instant Q is equal to V naught C into sin omega t. So charge at any instant on the capacitor is given by Q is equal to V naught C into sin omega t. So now therefore differentiate this with respect to time, that is dq by dt, dq by dt. We want current, so therefore dq by dt is equal to, that is V naught C sin omega t. Differentiation of sin omega t is cos omega t into omega. So that is dq by dt is nothing but I. So I is equal to V naught into C omega. Instead of that C omega, I will take that C omega into the denominator. It will become 1 by C omega into cos omega t. And since cos omega t can be done as sin omega t plus pi by 2. That is sin theta plus pi by 2 is cos theta, or cos theta is equal to sin theta plus pi by 2. So therefore I is equal to so dq by dt is I, understood? So I is equal to so this V naught divided by 1 C omega, I will call it as I naught into, so cos omega t instead of cos omega t, sin omega t plus pi by 2. So call this equation number 2, where I naught is equal to V naught divided by 1 by C omega. V naught divided by 1 by C omega is called peak value of current or maximum current. 1 divided by C omega, peak current or maximum current. So now comparing equation 1 and 2. Equation 1 is the EMF, alternating EMF applied to the capacitor, and equation 2 is the alternating current obtained in the capacitor. So alternating current in the capacitor, flowing in the capacitor, I is equal to I naught sin omega t plus pi by 2. Comparing equation 1 and 2, we observe that there is a phase difference between voltage and current in a pure capacitive circuit. There is a phase difference between voltage and current in a pure capacitive circuit, and current leads the voltage. And we observe that this is omega psi I is equal to I naught sin omega t plus pi by 2. That means current leads the voltage by an angle of pi by 2 in a pure capacitive circuit. In a pure capacitive circuit, current leads the voltage by an angle of pi by 2, or voltage lags behind the current. By an angle of pi by 2. Understood? So now the time diagram, that is the graph of variation of voltage and current. The graph of variation of voltage and current is drawn like this. That is with respect to time. So first applied voltage that is will remain same. So as in the previous derivations. So that is sinusoidal voltage V is equal to V naught sin omega t. So this is at 0, this is at pi by 2, and this is at pi, and this is 3 pi by 2, and this is 2 pi. Okay. So this is for applied AC voltage. That is V is equal to V naught sin omega t. Right. Okay. So now the current is ahead of the voltage. The current is ahead of the voltage by an angle of pi by 2. So in a pure capacitive circuit. So therefore the current has to be ahead, not behind. The current has to be ahead. So it will start from here. So I will draw the diagram like this. So like this you can draw. So this is for current, that is I is equal to I naught sin omega t plus pi by 2. So there is a phase difference of pi by 2 between current and voltage, So this is maximum, and here it is maximum, and here it is minimum. Understood? Okay. So thus, so in a pure capacitive circuit, the current leads the voltage by an angle of pi by 2. In a pure inductive circuit, current lags behind the voltage, because in inductor you will get the formula as I is equal to I naught sin omega t minus pi by 2 in the inductor, in the case of inductor. So therefore, in the case of inductor, current lags behind the voltage by an angle of pi by 2. In the case of capacitor, current leads the voltage by an angle of pi by 2. And now the phasor diagram. If you draw the phasor diagram, it is phasor for voltage. This is a phasor for voltage, so it represents V0, and this represents omega t, right? So V0 omega t. And now phasor for current, and current is ahead of voltage by an angle of pi by 2. So therefore, current will be drawn here. So this is current, that is maximum current I naught. From here to here the angle is pi by 2. Understood? So this will give the value of V0, and this will give the value of I naught, or you can relate that to the here also, same, no problem. So this is a phasor diagram. This is phasor diagram for a pure capacitive circuit. Phasor diagram for a pure capacitive circuit. Understood? That is voltage lags behind the current by an angle of pi by 2 in a pure capacitive circuit. Okay. So now capacitive reactance. Next concept, capacitive reactance. The equation, that is I naught is equal to V naught divided by 1 by C omega. Let 1 by C omega is equal to XC. Let 1 by C omega as XC. Take it as XC. So therefore you can write it as I naught is equal to V naught divided by XC. Compare this equation with I is equal to V divided by R. Then we observe that the XC has same dimension and unit, as that of resistance. XC has the same dimension and unit as that of resistance, and this XC is called as capacitive reactance. This XC is called as capacitive reactance. So what is capacitive reactance? The effective opposition offered by the capacitor, for the flow of current, AC current or just current, is called as capacitive reactance. The effective opposition offered by the capacitor for the flow of current is called capacitive reactance, and it is denoted by the XC and given by the formula XC is equal to 1 divided by C omega. XC is equal to 1 divided by C omega. Understood? And now for a DC current, so we know that for DC current, so that is a new frequency F is equal to 0. So therefore XC is equal to 1 divided by C into 2 pi F. 1 divided by C into 2 pi F. So XC is equal to 1 divided by 0. 1 divided by 0 is infinity. So thus capacitor offers infinite resistance to the DC current. That is, capacitor does not allow the DC current to pass through it. The capacitor does not allow the DC current to pass through it. So that is, the capacitor will cut off the DC current. And now for AC current, the value of frequency, that is frequency F is equal to some value, it is finite value, that is finite value. In India it is generally around 50 hertz, it is 50 hertz. So in some cases it may be 60 hertz or 40 hertz. So generally roughly it will be fixed 50 hertz. So f is equal to finite value. So therefore xc is equal to 1 divided by c into 2 pi into some finite value. So there is some value. So then so it is in the denominator. So therefore this value will be smaller value. So you will get a smaller value because it is in the denominator. Whatever the value comes, it is in the denominator. So therefore it will be a smaller value. So that is xc is smaller. xc is smaller for AC. For AC, that is the capacitance allows or capacitance offers least resistance or very less resistance, very less opposition to the flow of alternating current, whereas it gives infinite opposition to the flow of DC current. So that is capacitor cut off the DC current, whereas it allows the AC current to pass through it. Understood? So this is how we can understand. And now the variation of XC with frequency. If you draw a graph of variation of XC with frequency, the graph obtained will be a curved line like this. So that is because as frequency increases, the value of XC will decreases because XC is inversely proportional to frequency. XC is inversely proportional to frequency. So therefore graph obtained will be like this. Understood? So this is capacitive reactance. So what is capacitive reactance? Did you understood? So that is the effective opposition offered by the capacitor for the flow of current, alternating current, is called as capacitive reactance. And the SI unit and dimension of capacitive reactance is the same as that of resistance. And the capacitive reactance will be infinite for DC current and capacitive reactance will be less for AC current. Understood? Okay. So like in the inductor it will be reverse. In the inductor does not allow the AC current to flow. The inductor will allow the DC current to flow. Understood? Okay. So that we have to understand properly. Okay. So this is about alternating voltage applied to a pure capacitor. Understood? Okay. So in all these three derivations we have understood. Alternating voltage applied to a resistor, alternating voltage applied to a inductor, and alternating voltage applied to a capacitor. So now let us understand. Alternating voltage applied to all the three. That is series LCR circuit. Let us understand series LCR circuit. So this is also 5 marks derivation. Remember this, these three derivations, that is alternating voltage applied to a resistor, alternating voltage applied to a inductor, alternating voltage applied to a capacitor. These three derivations each carries 5 marks and they are important for exam, and as well as next 5 marks derivation. This is also one more 5 marks derivation, series LCR circuit. I will write the heading as series LCR circuit. Now we have to find the opposition offered by the circuit containing inductor, capacitor and resistor. The opposition offered by the circuit containing inductor, capacitor and resistor. Understood? Okay. So now let us consider a resistor of resistance capital R and a capacitor of capacitance C and a inductor of inductance L connected in a series, with a AC supply, as shown in a figure. Okay. Let us consider a resistor of resistance capital R, a capacitor of capacitance C and a inductor of inductance L are connected in series to a AC source, as shown in the figure, and this circuit is called as series LCR circuit. Okay. So now we have to derive the effective opposition offered by all the three, the effective opposition offered by all the three to the, that is all the three, resistor, capacitor and inductor, to the flow of AC. So now first the let V be the RMS value of voltage applied to the circuit. Let V be the RMS value of voltage applied to the circuit, and it is given by V is equal to V naught sin omega t, and I be the RMS value of current flowing through the circuit. Let I be the RMS value of current flowing through the circuit, and V be the RMS value of voltage, that is AC voltage applied to the circuit. Then the potential difference across resistor, the potential difference across resistor capital R is VR is equal to I into capital R. VR is equal to I into capital R. And this potential difference is in phase with I, that is IRMS. It is IRMS. It is same as IRMS, RMS value of current. Okay. This potential difference, that is potential difference in a resistor, in a pure resistive circuit, the voltage and current both are in phase. We have already studied there is no phase difference between voltage and current in a pure resistive circuit. So this potential difference is in phase with current I. So therefore, so they are represented along x axis, along one axis, that is x axis, only along one line. So it is along x axis as shown in a figure. So it is, we have to draw a graph also. Along with the derivation only I am drawing the graph. Not completely. I am drawing the graph as the derivation progresses. As the derivation progresses, I will keep on drawing the diagram. Okay. First we have calculated the potential difference across the resistance, and it is given by VR is equal to I into R, and we have already studied that the potential difference and current both are in phase in a pure resistive circuit. So therefore, this VR, this potential difference across the resistor is in phase with current flowing in the circuit. So they are represented along only one axis, that is along x axis I will take. So this is potential difference VR, and here only the current I. So both potential difference VR and current I both are in the same. So along x axis, so I will say this as x axis. Okay. Okay. Now next the potential difference across capacitor, the potential difference across capacitor C is VC is equal to I into XC. VC is equal to I into XC. What is XC? XC is nothing but inductive reactance, that capacitive reactance. XC is capacitive reactance. I is the current flowing through the circuit, that is these all are in series, so therefore the current will be same. The current flowing through resistor, capacitor and inductor will be same, but potential difference will be different. So here potential difference is I into R, and here potential difference is I into XC, and here potential difference will be I into XL. So potential difference will be different in a series connection. That's all we have studied in the current electricity only. Understood? And this VC is equal to I into XC, and this potential difference, that is VC is lags behind the current, lags behind the current I by pi by 2. So it is represented along say something is has O. So it is represented along x-axis as, okay, say it as OA. Say it as OA along x-axis, along this one as OB. Say it as OB. So as shown in figure. As shown in figure. So that is, so potential difference pi by 2. From here to here the angle pi by 2 means it will be here only. So this is the VC. This is the VC. So this will be the VC. So from here to here the angle will be pi by 2, no? From here to here the angle will be pi by 2. So along VC and say this as B, OB, right? And now as shown in figure. So now the potential difference across the inductor. The potential difference across the inductor. It is inductor L is VL is equal to I into XL, where XL is the inductive reactance, and this potential difference is ahead of current by an angle of pi by 2. We have already studied in a pure inductive circuit the potential difference leads the current by an angle of pi by 2, and in a pure capacitive circuit the potential difference lags behind the current by an angle of pi by 2. This VL is ahead of current by pi by 2. So it is represented along OD, say OD as shown in figure. That is current is here, so by an angle of pi by 2. So from here the angle of pi by 2 will be here only. So therefore, so this is okay. So this is VL, okay. This is VL. So first this is VR, okay, and this is VB, and this is VL. Understood? Okay. Now the resultant of all these three, the resultant of VR, VC and VL we want. Since VL and VC are in opposite direction, so therefore first find the resultant of VL and VC. The resultant of VL and VC, the resultant of VL and VC is VL minus VC. I will take it as VL minus VC by considering VL is greater than VC or XL is greater than XC. By considering that XL is greater than XC, the resultant of VL and VC will becomes VL minus VC. Remember that we have taken XL as greater than XC, so therefore the resultant of VL and VC will be VL minus VC. If XC is taken as greater than XL, if XC is taken as greater than XL, then resultant will be VC minus VL. Resultant will be VC minus VL. Understood? So, and this resultant will be represented. This resultant will be along largest one. Largest one is VL. So, this resultant is represented along OD. It is here. So, that is VL minus VC. VL minus VC. Understood? Okay. And it is along OB, OC, say OC, and it is along OC. Okay, say this point as C. Okay. And now the resultant of VL minus VC and VR. Shall I remove this diagram? Okay. Now we want resultant of VL minus VC and VR. The resultant of VL minus VC and VR is let us take it as V, is V and it is along, and it is along, that is, so it has to be VR is here and VL minus VC is here, so resultant must be in between them. So the resultant of two vectors, that is two phasors, will be in between them, that is V. So V, and so this is the resultant. Okay, let us take like this. Okay. So now it is the resultant, and it is along O, say some C, B, C, D, E, F. Okay, OF. It is along OF, along OF. Understood? And now from this right angle, from this triangle, from this right angle triangle, so by applying that is parallelogram law of factor addition, by applying a parallelogram law of factor addition, we can apply the law of factor addition, parallelogram law of factor addition to all these, that is voltage and current. All these are voltages. There is potential difference across inductor, potential difference across capacitor, and a resultant of potential difference across inductor and capacitor, that is VL minus VC, and potential difference across resistor. All these are scalars, but by writing the phasor diagram, we can apply the vector addition laws. We can apply the laws of vector addition, which I told already while explaining about the phasor diagram. So now the resultant of VL minus VC and VR is V, and it is along OF. So now by applying parallelogram law of factor addition, we get OF square is equal to under root of OF square is equal to, that is this square plus this square, that is OA square. You say OA square plus AF square plus AF square, and AF is the same as AC. AF is same as AC. So OF square is equal to under root of OA square plus OC. This is A, AF will be same as OC. So OC square. So now substitute their values. OF represents V, effective potential difference, that is V, under root of OA represents what? OA represents VR, that is VR square plus OC represents VL minus VC, so VL minus VC whole square. Understood? Now substitute their values. Now substitute the values of VR, VL and VC. Substitute VR, VL and VC values. So then V is equal to under root of VR is equal to I into R. So I into R whole square, that is I square R square, plus VL I into XL, VC I into XC whole square, right? And now I square taken common. I square comes here, and I square is taken common and taken out of the root, and then you will get V is equal to I under root of R square plus XL minus XC whole square, R square plus XL minus XC whole square, and now V divided by I is equal to under root of R square plus XL minus XC whole square, but V divided by I is nothing but effective opposition, that is impedance, but V divided by I is equal to Z, that is impedance of LCR circuit. I will say this as impedance of LCR circuit, that is effective opposition offered by the series LCR circuit to the flow of current. The effective opposition offered by the series LCR circuit to the flow of current is called as impedance, and it is denoted by Z. So therefore Z is equal to under root of R square plus XL minus XC whole square. So this is the expression for impedance of series LCR circuit. Impedance of series LCR circuit. The impedance of series LCR circuit is given by Z is equal to under root of R square plus XL minus XC whole square, where R is the resistance, XL is the inductive reactance, XC is capacitive reactance, and Z is the impedance of LCR circuit. So what is impedance of LCR circuit? The effective opposition offered by the LCR circuit to the flow of current is called as impedance, and it is denoted by Z. It is denoted by Z. Understood? Okay. So now drawing a impedance triangle. If you take this triangle, right angle triangle, it is I will draw the impedance triangle. From that only we will draw the impedance triangle. It is OAF. OAF. Take the triangle OAF. OAF. So OA represents VR. So instead of VR I will write it as resistance capital R. Okay. And AF is the same as OC, and it represents VL minus VC. Instead of VL minus VC we write it as XL minus XC. And OA represents V, and V is equal to that is I into R. So V, so therefore that is impedance. So that will be impedance Z. So this is phi. So let us take this angle as phi. This angle as phi. Understood? Where phi is the phase difference. Phi is the phase difference between resultant voltage and the current. The resultant voltage and current has a phase difference of phi in a series LCR circuit. Understood? And this is called impedance triangle. Instead of potentials, we are writing impedances. So the VR is represented along OA. So instead of VR, I will write R. So OEF, VL minus VC. Instead of VL minus VC, I will write XL minus XC. And OEF represent V, and impedance of that is effective voltage. So effective impedance, effective opposition. That is effective opposition is Z. Understood? Okay. This is called impedance triangle. Understood? Okay. So this is a derivation for series LCR circuit. Understood? And now for RL circuit. Now if the circuit is only RL, it is case number 1. I will write some case number 1. So if XL is equal to XC, then that is the inductive reactance is equal to the capacity, is equal to minus A, okay, in the derivation. If inductive reactance is equal to the capacitive reactance, then Z is equal to under root of R square plus 0. So therefore Z is equal to R. That is the impedance of LCR circuit will be same as that of resistance. So it can be called as pure resistive circuit. It can be called as pure resistive circuit. Understood? So case number 2. If XC, that is XC impedance, capacitive impedance is 0, that means capacitor is not there. So it is RL circuit. It is RL circuit. And then Z is equal to under root of R square plus XL minus XC. XC is equal to 0. So XL square. So Z is equal to R square plus XL square. So this is expression for impedance in a LR circuit. It is expression for impedance in a LR circuit. Understood? If they ask in the exam, okay, instead of asking LCR circuit, they will ask derive an expression for impedance of LR circuit. Then derive this one and then tell that if capacitance is 0, if the capacitance is not there, XC is 0, then Z is equal to under root of R square plus XL square. Understood? Like this also you can do. Otherwise, you can do fresh derivation only by considering a inductor and a resistor. That also possible. So very easily you can do it. Okay. Now this is called pure. Not pure. So inductive resistance circuit. So now case number 3. If XL is equal to 0, that is inductor is not there. Then it is RC circuit. Then it will be called RC circuit. So for a RC circuit, the impedance is given by Z is equal to under root of R square plus minus of xc whole square. So minus into that is whole square is there. So r square plus xc square. This is impedance of RC circuit. This is impedance for RC circuit. This is impedance for LR circuit, and this is impedance when XL is equal to XC. That is capacitive reactance and inductive reactance are equal. Then you can write this formula. Understood? Okay. Understand this derivation. This derivation carries 5 marks, and it is very important for theory exam. Very important for theory exam. These there are 4 derivations totally. It is AC voltage applied to resistor, AC voltage applied to inductor, AC voltage applied to capacitor, and series LCR circuit. These 4 derivations they have asked many times in the theory exams. Understood? So try to do this one and again this series LCR circuit derivation, and while drawing this one diagram, you have to be very peculiar, very accurate about the what you are using here. Understood? This diagram can be drawn differently also. You can draw this diagram differently also, but whatever explaining over there and on the diagram must match each other. The diagram and explanation must match with each other. Understood? Okay. This is series LCR circuit, and let us study some more things related. So we have derived the effective impedance or effective voltage or resultant voltage in a series LCR circuit. And now one more thing we have to derive, that is phase difference between the effective voltage and current. What is the phase difference between the effective voltage and current in a series LCR circuit? The phase difference between the phase difference between effective voltage and current in a series LCR circuit. In series LCR circuit, CKT means circuit. Okay. So that is phase difference. That is nothing but this 5 we have to find out. And now from the right angle triangle, OAF, from impedance triangle, or you say impedance triangle, or from the right angle triangle. So here if you can write VL minus VC, this one, and this is VR, and this will be V. So from the impedance triangle or from the right angle triangle, so OAF. So we can write tan phi is equal to it is AF divided by OA, and AF is nothing but VL minus VC. AF divided by OA, and AF is nothing but VL minus VC, and OA is nothing but VR. So VL minus VC divided by VR. So therefore tan phi is equal to VL value. VL is I into XL, and VC is I into XC, and VR is I into R. Now I taken common, and I cancel, so you will get tan phi is equal to XL minus XC divided by R. So this will give the R phi is equal to tan inverse of XL minus XC divided by R. So this formula will give you the phase difference between the resultant voltage and current in a series LCR circuit. This gives the phase difference between resultant voltage and current in series LCR circuit. And this derivation we have did by taking XL is greater than XC. Remember that we have did by taking XL is greater than XC. So once in the exam they have asked, once in the exam in the question paper, I will tell you the question paper. Once they have asked derive series LCR circuit by considering XC is greater than XC is greater than XL, then Z will comes out to be like this. Z is equal to under root of R square plus XC minus XL whole square. Understood? And this phi is equal to that is phase difference between current and voltage. Tan inverse of XC minus XL divided by R like this. So this formula will also change. Both the formula will change when XC is greater than XL. Understood? So that derivation must be also able to, you must be able to understand, or you must be able to derive. So derive that one only. So this is the homework for you people. That is, derive an expression for impedance in the series LCR circuit by considering XC is greater than XL, and also derive the expression for phase difference. Understood? By considering XC is greater than XL, derive an expression for impedance in the series LCR circuit, and also derive the expression for phase angle between resultant voltage and current. Understood? Okay. So this much is enough for this series LCR circuit, and there are many more things we have to study about this one. We will study all that things in the next class. Understood? Okay.